Hello students, today we shall be discussing about optical fibers. Now basically optical and systems which are made out of optical fibers, and these systems, they make very superior light sources and detectors. And they usually undergo very low loss. That is approximately 0.1 decibels per kilometer. Now, the advantages associated with an optical fiber are one is the abundance of static material and low cost. The second one is small size and weight and flexibility. Small size and weight. Also flexibility. The third advantage is electrical isolation. And immunity to electromagnetic interface. Electromagnetic interference. There is low transmission loss. And dispersion and wide bandwidth. And lastly, it has got there is a security, extra added security for putting off the transmitted information. That means those informations which are being transmitted through optical fibers, they have a security, and as there is an opaque shielding, around the fibers. So these are some of the advantages. Now, these optical fibers are mainly used in communications systems. And antennas. And we usually an LED, light emitting diode, or a laser is associated with this optical fiber, or is coupled with this optical fiber. Now, for transmission of data in either a digital or analog mode, the light source is current modulated. To impress the information out of the output. So, press the information onto the output. So there is a light goes to an optical fiber to a photo detector, and this optical fiber, it is progressively attenuated or distorted. Now, if the distance to be traveled is long, then what we require is something called an optical repeater. So, this repeater is nothing but a system where there is a source and then detector back to back. That means source and detector 1 and source and detector 2. So ST1 and ST2, there is a back to back coupling. Now, apart from this optical repeater, another thing that we require for a long distance travel is a boost given to the optical signals, and that boost comes from optical amplifiers. Optical amplifiers are RBM doped fiber amplifiers. EDFA. They are used to boost the signal. Now the basic fiber optic systems topologies. There are three types of fiber optic system topologies. So, fiber optics system topologies. There are three types. One is called the link. So let's look at this. Another is called multipoint. And the third one is called the network. Like that. Coming to the fiber types and modes. An optical fiber is a circular dielectric waveguide for transmission of electromagnetic signal. So there are three layers to an optical fiber. First one is called the core. It's the core, which is surrounded by the cladding, and which is again surrounded by an encapsulation. So this is the core, this is the cladding, and this is the encapsulation. The core is having a refractive index almost equal to 1. The cladding is having a high refractive index. Cladding is having a refractive index NR2, and so this is not NR is equal to 1. This is NR1, and NR2 is usually greater than NR1. Whereas this encapsulation, it is nothing but an elastic plastic buffer. So basically a buffer made of elastic and plastic for strength and mechanical isolation. Strength and mechanical isolation. Now, an optical fiber has two types of modes. One is called fiber. It's called single mode. And another is called multi-mode. And it is determined by the core diameter. Type of mode will be. Usually multi-modes have a large core diameter. and its advantage is gets an advantage in coupling with an LED. And an ease of launching optical power. The fibers also can be classified as step index and graded index. And so basically in step index, the difference between step and graded index is here the NR1 and NR2 are clearly defined. So this is NR1, this will be NR2. Whereas in the case of a graded index, the decrease is gradual. That means that the code NR1 refractive index, I should say, is not as sudden. There is no sudden change in refractive index. It is graded. And advantage of having a graded index is that it reduces the intermodal distortion in the multimode fiber. So it reduces intermodal distortion. Mathematically, you can express NR as a function of distance from the center as equal to NR1 then 1 minus 2 delta R by A to the power S 1 by 2, where delta is nothing but NR1 minus NR2 divided by NR1. A is the fiber core. The core radius, and S here, this is the shape of the index profile. So if you look at a typical index profile, so it looks something like this. So you have a core surrounded by the cladding. The core is supposed to be at high refractive index, NR1, and this is at low refractive index, NR2. So NR1 is greater than NR2. So the index profile will look something like this. Whereas and this is for NR2 and this is for NR1. This distance from the center to the edge is around 100 micrometer, and this distance, the diameter of the core, is 5 to 10 micrometer. This one, 5 to 10 micrometers. And this is the step index. While in the case of threaded index optical fiber, the difference in refractive index is not so certain, but takes a little bit gradual. So just like this. So this is around 40 to 100 micrometer. Now, the material which are used for optical fibers, they are doped glasses. So when we have a glass which has been fused with a mixture of metal oxides, selenides, sulfides, and then these glasses make an optical fiber material. And the optical fiber in the IR region, it consists of silica, and to change the refractive index of the silica, that means to have a clear demarcation between NR1 and NR2, various oxides and fluorides are added to cause a little change in the silica glass refractive index, whereas in usual place the refractive index in silica glass varies from 1.445 to 1.475. So in addition to silica, we can also have halide glasses. An example being zirconium fluoride, aluminum fluoride, barium fluoride, and sodium fluoride.